This is an engine. But what are the different parts that make up the engine? What are those parts made of? How are they made? And how does the engine work? Let's start at the heart of the engine, where we have the engine block. The engine block is typically made from cast 3000 series aluminium manganese alloy. Aluminium alloys are favoured materials across the engine due to low density for weight saving, high thermal conductivity for cooling, and corrosion resistance. The engine block houses the lower parts of the engine, including the cylinders, which are formed by machining cylindrical bores out of the block. Inside the cylinders sit cylinder liners, usually 3 to 6 mm in thickness and made from cast steel alloyed with vanadium and titanium, although many engines use a coating on the inside of the cylinder walls instead of separate liners. Either way, the purpose is to provide a tight seal between the piston and the cylinder wall, to provide a smooth surface for the piston to glide against, and to provide abrasion resistance. The relatively low thermal expansion coefficient and high hardness of steel compared to aluminium alloys are ideal for this. The pistons sit inside the cylinders and are typically made from cast or forged 4000 series aluminium silicon alloy. The low density of aluminium alloys is especially important for moving parts of the engine, such as the pistons, in order to minimize inertia and resistance to movement, while the alloy with silicon provides the strength and toughness required right in the firing line of combustion. Piston rings usually come in threes, which fit around the head of each piston. The piston rings play a similar role as the cylinder liners, forming the seal between the piston and the cylinder wall, and therefore, like the cylinder liners, are usually made from cast steel alloyed with vanadium and titanium for hardness to resist abrasion, and for low thermal expansion coefficient, so to maintain a tight seal across a range of operating temperatures. Thickness of each ring is usually 0.8 to 1 mm. The upper two rings are known as compression rings and serve to seal the combustion chamber above the piston. The lower ring is known as the oil ring and serves to prevent lubricating oil in the cylinder below the piston from seeping into the combustion chamber. The upper surface of the piston is called the piston head. The overhung side of the piston is called the piston skirt. The piston skirt houses a hollow tube called the piston pin. Piston pins are typically made from forged, quenched, tempered and surface hardened 4340 steel, which is a chromium, molybdenum and nickel alloyed steel. Surface hardness for abrasion resistance is one of the priorities of piston pins. The piston usually has a diameter of 80 to 83 mm, while the piston pin is offset from dead center usually by 1 to 1.5 mm. The smaller end of the connecting rod attaches to the piston pin, around which it is free to rotate. The resulting friction between the connecting rod and the piston pin is the reason for the specification of surface hardness on the piston pin. Like piston pins, connecting rods are typically made from forged, quenched, tempered and surface hardened 4340 steel. Connecting rods are amongst the most stressed parts of the engine and therefore are typically forged rather than cast to avoid casting defects, such as voids and non-uniform grain structure that weaken the material, and are typically made from steel rather than aluminium alloy, where aluminium alloy is around 1/3 the density, which is especially desirable for moving parts, but is also around half the strength, 1/3 the stiffness, and has a limited fatigue life, which means over repeated loading cycles, the material becomes weaker and will eventually fail, whereas for steel, provided a critical load is not reached, it will not fail. Since the connecting rods are constantly loaded through compression and tension when the engine is running, these properties are of utmost importance and make steel the preferred choice, although for high-performance engines, machined billet 6000 series aluminium magnesium silicon alloy may be used, where the lower strength and stiffness compared to steel is offset by thicker material from around 12 mm up to around 16 mm, although at greater financial expense, while still benefiting from a 20 to 30% weight saving, and while the limited fatigue life is justified by the willingness to replace the connecting rods more frequently, although again at greater financial expense. The larger end of the connecting rod attaches to the crankshaft, around which it is free to rotate. As the piston moves up and down the cylinder, vertical movement of the piston is transferred into rotation of the crankshaft via the connecting rod. The crankshaft is divided into offset subsections from the main shaft, called crank pins, which the connecting rods attach to. Counterweights on the crankshaft balance the opposing weight of the pistons to ensure smooth rotation. The crankshaft is usually made from forged, quenched, tempered and surface-hardened 4140 steel, which is similar to the 4340 steel but with less carbon and without the nickel addition. For high-performance engines, 4340 steel is typically used for its higher strength and toughness. The crankshaft is usually the second largest part of the engine after the engine block, and so substitution for a lower density material such as aluminium alloy may seem like a good idea, especially since, unlike the engine block, the crankshaft is a moving part which will also benefit from the reduction of inertia. However, in practice, non-ferrous crankshafts are rare, even for high-performance engines, since the strength, stiffness, hardness, and low fatigue susceptibility of steel make it difficult to beat for crankshafts. The flywheel is a disc which attaches to the transmission end of the crankshaft. As the crankshaft rotates, the flywheel rotates. The other side of the flywheel attaches to the transmission system, which goes on to transfer rotation of the crankshaft into rotation of the car's wheels. Like the crankshaft, and for the same reasons, the flywheel is typically made from cast or forged, quenched, tempered and surface-hardened 4140 or 4340 steel. The flywheel is an energy storage unit, which has the primary function of storing and smoothing out jerky and pulsating rotational energy of the crankshaft by using the inertia effect of the flywheel's mass. The mass of the flywheel increases its inertia and keeps it spinning at a relatively constant speed despite the pulsating movement of the pistons. The head gasket is a thin strip, usually consisting of 3 layers of carbon steel sandwiching elastomer with a total thickness of 1 to 2 mm. The primary purpose of the head gasket is to seal the gap between the engine block and the cylinder head by accommodating for differences in thermal expansion coefficient between the two. The cylinder head houses the upper parts of the engine. In common with the cylinder block, the cylinder head is typically made from cast 3000 series aluminium manganese alloy. The inlet manifold splits into inlet ports, with each port connecting to one cylinder via the cylinder head. The inlet manifold delivers air to the cylinders and is typically made from cast 3000 series aluminium manganese alloy or injection molded glass fiber reinforced plastic composite. Fuel injectors spray a fine mist of fuel into the incoming air to achieve an optimal air-fuel mixture. Port injection was once common amongst petrol engines, with one fuel injector per inlet port. The fuel injectors are usually made from machined austenitic stainless steel for corrosion resistance. The exhaust manifold routes the hot pressurized exhaust gases away from the cylinders after combustion and eventually to the tailpipe. The exhaust manifold is typically made from cast austenitic stainless steel, where high temperature corrosion resistance is the main priority. High performance engines may use seamless tubes, extruded from stainless steel or even titanium, aluminium, vanadium alloy, which is around half the weight. There must be at least one inlet valve and one exhaust valve per cylinder, although most engines use 2 inlet valves and 2 exhaust valves per cylinder, giving a total of 4 valves per cylinder. Valves open and close by moving downwards and upwards respectively. The inlet valves allow air-fuel mixture to enter the cylinder from the inlet manifold, while exhaust valves allow combustion gases to exit the cylinder to the exhaust manifold. Inlet valves are typically made from machined austenitic stainless steel for corrosion resistance at up to 500 degrees centigrade. Exhaust valves have to withstand even higher temperatures of up to 900 degrees centigrade, as well as higher pressures, and so typically use a higher grade austenitic or even martensitic stainless steel with nickel additions for heat resistance. High performance engines typically use valves made from titanium, aluminium, vanadium alloy. In petrol engines there is a spark plug. The spark plug sits at the centre of the cylinder head and has the job of providing an electrical spark to ignite the air-fuel mixture. Spark plugs usually consist of a copper core which conducts electricity to the central electrode made from high temperature resistant nickel alloy. For high performance engines, a platinum or iridium plate is often added to the central electrode tip, which can withstand the higher temperatures of the more potent combustion. Electricity is arced from the central electrode to the ground electrode, also typically made from nickel alloy, resulting in a spark. The assembly is housed in an alumina ceramic casing. The non-conductive ceramic casing ensures the spark occurs at the tip of the central electrode, which protrudes into the cylinder. Its low thermal conductivity also helps to maintain temperature at the tip of the central electrode for optimal combustion. Diesel engines do not have a spark plug, since diesel is much less flammable than petrol, so much so it does not ignite when exposed to a spark. Instead, diesel relies on temperature and pressure of intense compression to initiate combustion. Thus, petrol engines are called spark ignition engines, while diesel engines are called compression ignition engines. Port fuel injection was once common amongst petrol engines, while diesel engines have almost always used direct injection, with the fuel injector moved from the inlet port to directly inside the cylinder head, usually at the top of the cylinder head in the place of where the spark plug is found in a petrol engine. Most modern petrol engines also use direct injection, with the injector either at the top of the cylinder head alongside the spark plug or at the side of the cylinder head between the inlet valves. Some modern petrol engines even use combined port and direct injection, which is known as dual injection. The valve train is housed inside the cylinder head and consists of camshafts, cams, and the valves themselves. The camshafts hold cams, which are offset lobes protruding from the camshafts and regulate opening and closing of the inlet and exhaust valves. As the camshafts rotate, the offset section of the cam contacts the valve is pushed down via the spring and the valve opens. As the rounded section of the cam contacts the valve is allowed to rise back up and the valve closes. Dual overhead camshafts, as shown here, are common, with a set of two camshafts, one camshaft operating the inlet valves and the other operating the exhaust valves. Alternatively, one camshaft may operate both inlet and exhaust valves, although these days this is pretty rare. Camshafts and the cams are usually manufactured as one piece, either cast or machined and surface hardened 4140 or 4340 steel. The camshafts are connected to the non-transmission end of the crankshaft by a timing chain or belt. As the crankshaft rotates, the camshafts rotate in perfect synchronization with the crankshaft. This may be a smart way of automatically opening and closing valves, but it has limited functionality, operating in the same way across all conditions, with rotational speed of the camshafts and therefore frequency of valve opening and closing having to always be proportional to crankshaft rotational speed, and so is not ideal for achieving conflicting performance metrics such as fuel economy versus power. Variable valve timing, VVT, is a means of varying valve opening and closing behavior, mainly dependent on crankshaft rotational speed, which we call RPM, revolutions per minute. The three parameters of variable valve timing are frequency, that's how often the valve opens and closes; duration, that's how long the valve stays open each time; and lift, that's by how much the valve opens. As an example of the benefits of variable valve timing, at low RPM we may want to limit how much air-fuel mixture gets into the cylinder so to minimize combustion and maximize fuel economy. So we may want to have a low valve frequency, a short valve duration, and a small valve lift. At high RPM, we may want to pack as much air-fuel mixture into the cylinder as possible to maximize combustion and resulting power. So we may want to have a high valve frequency, a long valve duration, and a large valve lift. If we look at the dyno graph, which shows power against RPM, we can see the effect of variable valve timing at 4,500 RPM, increasing the gradient of the power curve. Variable valve timing in this way can be achieved by a wide range of methods, the most simple one being with gears on the timing chain which adjust the rotational speed of the camshafts relative to the crankshaft, and so adjust valve frequency. By switching over to a smaller gear at high RPM, the rotational speed of the camshafts increases, opening and closing the valves more frequently. More sophisticated systems use multi-lobe designs, where the camshafts have multiple sets of lobes with different profiles and/or sizes, and therefore offer variability of valve duration and valve lift. Depending on RPM and other factors such as engine temperature, the engine changes from one set of lobes to the other. There are various ways of doing this, with almost all engine manufacturers having their own system. One of the simplest versions, such as the shift cam technology used by BMW, works by shifting the camshaft backwards or forwards. Yet more complex systems, such as the VTEC system developed by Honda, which stands for Valve Timing Electronic Control, uses an additional rocker arm as the middleman between the lobes and the valve, with an electronically operated pin which moves in and out to hold the larger section of the rocker arm in place, which is then driven by the larger cam lobe and contacts the valve. Variable valve timing became very popular in the late 80s and early 90s, especially with Honda, as a means of squeezing more power out of a smaller engine, where road tax in Japan was and still is determined by engine size.